Hello everyone. Today we are going to present the topic Application of Eigenvalues and Eigenvectors in Science and Engineering. Eigenvalues and eigenvectors are among the most important concepts in linear algebra. Although they are often introduced as abstract mathematical ideas, they play a fundamental role in many real-world scientific and engineering applications. In many areas of science and engineering, complex systems are modeled using matrices. This matrix may represent physical systems, electrical circuits, mechanical structures, or datasets. Eigenvalues and eigenvectors provide a powerful way to analyze such systems and understand their behavior. The goal of this presentation is to explain what eigenvalues and eigenvectors are, why they are important, and how they are applied in practical scientific and engineering problems. In the first part, I will introduce the basic definition and intuition behind eigenvalues and eigenvectors. Then, my partner will explain two major applications: mechanical vibration systems and data analysis using principal component analysis. Finally, we will summarize their importance in science and engineering. Let us begin with the formal definition. Given a square matrix A, if there exists a non-zero vector V such that AV equals to lambda V, then lambda is called an eigenvalue of matrix A, and V is called the corresponding eigenvector. This equation tells us something very special about the vector V. When matrix A acts on V, the direction of V does not change, only the magnitude changes, and this change is controlled by the eigenvalue lambda. In contrast, most vectors change both direction and magnitude after a matrix transformation. Eigenvectors are special because they remain aligned with the transformation. From a geometric point of view, eigenvectors represent invariant directions of the transformation, while eigenvalues represent the scaling factors along those directions. This geometric interpretation is extremely helpful in understanding complex systems. In practice, instead of analyzing an entire matrix directly, engineers and scientists often analyze its eigenvalues and eigenvectors. This is because eigenvalues and eigenvectors capture the essential behavior of the system in a compact and meaningful way. In science and engineering, eigenvalues often have clear physical meanings. For example, eigenvalues can represent frequencies, growth rates, decay rates, or energy levels, depending on the context. Eigenvectors represent the corresponding modes, patterns, or directions associated with these quantities. Because of this interpretation, eigenvalues and eigenvectors are widely used to analyze system stability and dynamic behavior. In many systems, the sign and magnitude of eigenvalues determine whether the system is stable or unstable. A system with eigenvalues that have positive real parts may grow uncontrollably, while a system with negative real parts tends to decay and stabilize. This type of analysis is fundamental in engineering design, where safety and reliability are critical.
I will now introduce the first major application, mechanical vibration systems. Mechanical vibrations occur in many engineering structures, such as buildings, bridges, machines, vehicles, and aircraft. These vibrations may be caused by external forces like wind, earthquakes, engine operation, or moving roads. Engineers model these systems using physical laws. which often lead to systems of differential equations. These equations can be written in matrix form. When these matrix equations are analyzed, eigenvalues and eigenvectors naturally appear. The eigenvalues of the system correspond to the natural frequencies of vibration. Each natural frequency represents a frequency at which the system tends to vibrate naturally. The eigenvectors correspond to the mode shapes, which describe how different parts of the structure move relative to each other during vibration. The information is extremely important in engineering design. If a structure is excited at a frequency close to one of its natural frequencies, resonance may occur. Resonance can cause very large vibrations, leading to discomfort, material fatigue, or even structural failure. By calculating eigenvalues and eigenvectors, engineers can predict this dangerous situation and design structures that avoid resonance. As a result, eigenvalue analysis is widely used in civil engineering, mechanical engineering, and aerospace engineering to ensure safety and performance. Another important application of eigenvalues and eigenvectors is in data analysis, is battery principal component analysis, also known as PCA. In modern science and engineering, large data sets are very common. These data sets may contain many variables, making analysis difficult and computationally expensive. PCA provides an efficient method to reduce the dimensionality of data while preserving the most important information. In PCA, we first construct a covariance matrix that describes the relationships between variables in the data sets. We then compute the eigenvalues and eigenvectors of the covariance matrix. The eigenvectors represent the principal directions of the data, while the eigenvalues represent the amount of variance associated with each direction. By selecting only the eigenvectors with the largest eigenvalues, we can represent the data using fewer dimensions. This process reduces noise, improves efficiency, and it makes visualization easier. PCA is widely used in image compression, facial recognition, pattern recognition, and machine learning. In addition to mechanical vibration systems and data analysis, eigenvalues and eigenvectors are also widely used in Markov chains and steady state analysis, which appear in many scientific and engineering applications. A Markov chain is a mathematical model used to describe systems that move between different states according to certain probabilities. Examples include population movements, web page ranking, communication networks, and queuing systems. These systems can be represented using a transition matrix, where each entry describes the probability of moving from one state to another. In this context, eigenvalues and eigenvectors help us understand the long-term behavior of the system. In particular, the eigenvector corresponding to the eigenvalue lambda equals 1 represents the steady-state distribution of the Markov chain. This steady-state factor tells us how the system behaves at a long period of time, regardless of its initial state. For example, in web search engines, a similar idea is used in ranking web pages. The importance of each web page can be modeled as a state in a Markov chain, and the steady steady-state factor tells us how the system behaves after a long period of time, regardless of its initial state. For example, in web search engines, a similar idea is used in ranking web pages. The importance of each web page can be modeled as a state in a Markov chain, and the steady-state eigenvector represents the relative importance of each page. By computing eigenvalues and eigenvectors, engineers can determine which pages are most influential in network. From an engineering perspective, this type of analysis is extremely useful. It allows engineers and scientists to predict long-term trends, analyze system stability, and make informed decisions based on probabilistic models. Once again, eigenvalues and eigenvectors provide a powerful way to simplify complex systems and extract meaningful information from them.
Beyond mechanical systems and data analysis, eigenvalues and eigenvectors are used in many other scientific and engineering fields. In electrical engineering, they are used to analyze circuit behavior and power systems. In control engineering, they help determine system stability and response characteristics. In physics, especially quantum mechanics, eigenvalues represent measurable physical quantities such as energy levels. This demonstrates that eigenvalues and eigenvectors are universal tools across science and engineering. Their ability to simplify complex systems makes them indispensable in both theoretical analysis and practical applications.
In conclusion, eigenvalues and eigenvectors are not merely abstract mathematical concepts. They are powerful analytical tools that connect linear algebra with real-world applications in science and engineering.
Through examples such as mechanical vibration analysis and principal component analysis, we can clearly see how these concepts are applied in practice. By understanding eigenvalues and eigenvectors, engineers and scientists are able to analyze complex systems, improve designs, and make informed decisions. Thank you very much for your attention.